Hello everyone, welcome to week 2. In week 1, we focused on LLM foundations and we learned how LLMs work internally. We saw how we can build general purpose LLMs, train them and use them to power chatbots. Now in this week, our focus would be on building a customer support chatbot. So along the way, we would learn all the techniques and topics that are very important to make this possible. In particular, we will talk about how can we adapt LLMs, meaning we go from general purpose LLMs, which we saw in week 1, to specialized LLMs. And we would learn various techniques and topics here, such as fine-tuning, prompt engineering, and Retrieval-Augmented Generation, or RAG. And then we'll zoom in to RAG and learn all the components of it, how it can be built, and its system design. And finally, we'll have project 2, which is a hands-on exercise to build a customer support chatbot using all the techniques we learned and available tools and libraries. So let's start. The first question that we want to answer is, why should we bother ourselves? Why even adaptation is needed? And to better understand that, let's see some examples. So imagine this is a general purpose LLM and we have some general purpose use cases. For example, we can ask this LLM some math questions like what is 2 plus 2? Or we can ask brainstorming questions like, help me write an email to my manager to ask for time off. Or we can also ask coding questions like, my code is not running, read it and fix the bug with the code. And then the LLM would process these inputs and it's very likely to answer these questions correctly. And the reason for that is because it has seen a lot of similar examples in its training data, so it already knows how to answer these questions. Now, imagine we use this same general purpose LLM and ask some specific use case. So let's say we have a retail store and we want to have an LLM and offer it as a chatbot to our customers. So the customers can easily ask relevant questions and the LLM should answer that. Now, if a customer for our retail store asks our LLM a question like, what is your refund policy? The LLM is very likely to hallucinate, meaning that it would generate something that is not accurate or correct. Let me go to ChatGPT and see a real example. Let me ask a question like, what is your refund policy? And this is basically a common question that our customers may want to ask us. So our LLM, it's very important to be able to answer it correctly. Now, if we use a model like ChatGPT to serve our customers, this is what ChatGPT would respond. OpenAI's refund policy depends on the situation and how the purchase was made. So basically, this model is answering this question and assuming that my question is about OpenAI. So it's not going to really answer the question based on the retail store that we have in mind. Now, if I ask another question like, what is, how long shipping take? How long does the shipping take? Could you clarify what you are referring to? For example, so basically it's OpenAI model is very smart. So it asks for clarification because it knows that this prompt is ambiguous. But a lot of LLMs may not even ask that and may just start hallucinating and just throwing out some numbers, which is obviously incorrect. So that's the problem. That's why we want to adapt LLMs. Basically, we want to adapt an LLM to a domain-specific use case, such as retail store. So when these questions come to the LLM, like what is the return policy, how long does the shipping take, and what is the contact of customer service, the LLM can respond to this. More formally, we have a problem statement, which is adapt a general purpose LLM so it can accurately answer questions in a specific domain using additional documents. So basically, let's say we have a retail store and we have a bunch of internal documents or knowledge base. And then this can be anything like PDFs, it could be images, HTMLs, Wikipedias, and so on. And then we want this to start from this general purpose LLM and somehow adapt it. So when questions come, the LLM can use this information to answer the question. For example, if a question comes like, what is the refund policy? The LLM should answer based on the document database. You can return items for any reason within 30 days of your purchase. So this is the goal. And there are different techniques that this adaptation is possible. Three main techniques that we would learn is first, fine-tuning, second, prompt engineering, and third, retrieval-augmented generation, or RAGs for short. We would learn about each of these, and we discuss the limitations and strength of each technique. All right. The first way to adapt an LLM is fine-tuning. And it's basically the most obvious way to adapt a general purpose LLM into a specialized LLM. And the idea behind it is to continue training the general purpose LLM on our document database. And document database is basically our internal knowledge base, or it could be a bunch of PDFs, images, HTMLs, Wikipedias, and things like that, which we want to ultimately the LLM to learn from and can answer according to them. So after we train the general purpose LLM on this document database, we would get this output, which is a specialized LLM. Now, this specialized LLM is ready to be used. It's basically having the tuned weights, and those tuned weights allows it to produce responses according to this provided document database. So after it's trained, it can be used. For example, if we ask questions like, what is the return policy? It would be able to answer, you can return items for any reason within 30 days of your purchase. And basically this answer is coming directly from its learned weights, or in other words, from its compressed knowledge of the new training data that we use to train. If we also ask questions like, how long does the shipping take? It may answer typically 14 days. And so on. Now, there are two options to fine-tune the LLM, and we have them here. Option one is we update all the parameters of the LLM, and option two is basically parameter-efficient fine-tuning, which refers to a set of techniques that do not update all the parameters of the LLM. So we would learn about both of these in a second. So updating all the parameters, as the name suggests, is very obvious. We allow the training algorithm and the optimizer to tune all the weights inside the LLM as it's being trained on the training data. So remember, LLM has these blocks, and each block has attention layer, MLP layer, and so on. And then each MLP is basically two linear layers, and each linear layer has their own weight. So when we are updating all the parameters, the optimizer may go back and just change or tune a little bit each of these weights, so that the model can better answer given its new data set. However, the problem with this approach is that it can be very expensive. Remember, LLMs might have billions of parameters, so training an LLM and allowing the training algorithm to update all its parameters, it means that it can be computationally very, very expensive. And because of that, we have the second option, which is parameter-efficient fine-tuning. Parameter-efficient fine-tuning is basically referring to a set of techniques that allows us to adapt an LLM and fine-tune it without updating all its parameters. Basically, the idea is to only update a subset of parameters or a small number of parameters. And again, there are different techniques that allows us to do that. For example, we have adapters, we have LoRa, prompt tuning, activation scalars, bias only, sparse weight deltas, and so on. And then the first two are very popular and widely used, adapters and LoRa. So we'll zoom into these two and understand how they work internally. And then there are some other papers and interesting reads for other methods, so which you can refer to later. So let's start with adapters. So the idea behind adapters is very simple. It says that instead of updating all the parameters of the LLM, we just freeze them, meaning that we do not allow the optimizer to update them during training. So this is gray, means that they are frozen. We are not really updating their weights. And then we inject some new trainable layers inside this architecture. So for example, between these, we can add 3 more layers in red, and red means we allow the optimizer to update its weights. And then we train this model on the training data. So all these weights of the original LLM would remain unchanged. And then everything new would be learned such that whenever we have a new prompt, the prompt now can be answered according to the dataset using these newly learned weights. And then this is the initial paper. It was released in 2019, Parameter Efficient Transfer Learning for NLP. If you are interested to understand the details of it, you can take a look at this paper. But what they are doing, basically, they are just injecting these adapter layers inside the transformer architecture, and then they train it on their new data to adapt the LLM for a new task. So it's going to be an interesting read. You can take a look at it, but high-level idea is the same. It just goes into the transformer architecture, and then after attention and MLP, it just adds an adapter layer. So that's all the change, and only adapter layers are learned during fine-tuning, and everything else is frozen. So this is adapters. Now, the other approach is LoRa. This is basically another technique which was introduced after adapters. And it's kind of following a very similar style. The idea is to add some new weights such that we can freeze the rest of the model and only learn those new weights. And the way it does this is by introducing two low-rank matrices, and it refers to them as the LoRa layers. So let's understand what that means. Again, an MLP layer has two linear layers, and if we now zoom in into this linear layer, it transforms some input to output, and then internally it stores a weight, and it's just a weight matrix of size d out by d in. D out is the dimension of the output, d in is the dimension of the input. Now, what LoRa does is injects layers here. So it basically targets all the linear layers inside the model, and then it keeps it frozen. So everything in this branch is as normal. X goes still into the same linear transformation. The weight is frozen, so it's not being changed. And then the output is WX. But now it also adds two low-rank matrices, B and A. And then the idea is to also pass the X in this branch. And this branch also transforms X, and the output is ABX, if we just think of it mathematically. And then this ABX would have the same shape of WX. So we can just add them up, and then it forms the final output. And these two newly introduced matrices are learnable, meaning that the parameters can be tuned during the training. So these are LoRa layers. And it's very powerful technique. It also has some advantages over adapters. And if you are interested, this is their original paper, LoRa, low-rank adaptation of large language models. And then they talk in detail about this. But again, the high-level idea is to target all the linear layers and just add this branch with two low-rank matrices and only learn those matrices and freeze everything else. And again, they discuss why this method has some advantages over adapters and why at inference time it's faster. But that's the high-level idea, and it's very powerful technique. Now, there are lots of libraries that allows us to apply some of these parameter-efficient fine-tuning techniques. One popular library is Hugging Face PEFT, and it basically just gives you a set of tools that we can easily wrap a model and introduce new layers or new parameters to it and train the model such that only those layers gets updated. So this is just, you can take a look at it. It has some numbers and talks about advantages and so on. And then here I have also a very short demo to see how it looks like in practice. So this is my Jupyter notebook, and here basically I can use I can rely on PEFT and import some configs. Again, these are not important. What is important here is I can use the transformers library to pull a model. For example, here I'm pulling Qwen 2.5 3 billion instruct. It's basically a post-trained model by Qwen, and it has 3 billion parameters. So let me load this. It may take a while. Okay, so now we have this model, and this model, again, it's an instruct model. So we can inspect it here. If we print a model, it would show us all the layers. It has these layers, embed tokens, and these are the shapes, and it has layers and self-attention, things that are very like very normal things in a decoder-only transformer. And we have an MLP here with some linear layers and so on. We can also inspect these parameters to see if they are, to make sure they are 3 billion. So for that, if we print parameters, it would give us a generator. And then to just see the actual numbers, if we do something like this, P for P in model.parameters, let's just print this to see the shapes. So here we can see that these are the weight matrices of all different layers in the model. And in order to get the actual, the sum of all these weights, we can just do sum of all these. And this number is basically 3 billion, 3 billion, 85 million, and so on. And so it is consistent with the 3 billion naming. Now, let's say we want to, we loaded this model. Now we want to train it, but we want to use parameter efficient fine tuning, meaning that we don't want to really update all the parameters of this model. And for that, we can apply PEFT. So again, you can refer to the documentations to understand all the details and inputs. But at a very high level, what I'm doing here is basically I'm creating a config for LoRa. And once I have that, I have this wrapper, get PEFT model. I pass the initial model and the config that I created to get this new model. And now this new model is basically have these newly added LoRa layers and only trains those. So everything else is frozen. So if I print trainable parameters, it would say total parameters is this. And note that this is higher than this. And that's because now we are adding LoRa layers. Sorry, this is not the train. So the all parameters is this. And now note that this is higher than this slightly. And that's because we are having this additional LoRa layers. And only these many parameters are trainable. So it's very small compared to the 3 billion parameters. It's only 3 million. So only 0.1. This is the trainable percentage. Only 10% of the original, not 10%, 0.1% of the original parameters are trainable. So that's why it's a lot more efficient. We only need to learn these many parameters during training. And then now the model is ready. We can just simply use some data set to train it. And then once it's trained, we can save it. And we can just name it something. We can have the same name and the LoRa at the end. And then later at inference, we can just load this model instead of the original LoRa model. And it could be as easy as this. So we have PEFT model from pre-trained and then load our model. And then we can pass whatever input we have, what is the refund policy. And if we generate and decode, we would get responses. And those responses now are more consistent with the new data that were used to train this model. So I just showed this example to say that it's very easy in practice to utilize some of these methods and algorithms to fine-tune LLMs. So let's back to our lecture. We talked about fine-tuning, and we saw our two options, updating all parameters and parameter-efficient fine-tuning like adapters and LoRa. In the next lecture, we will switch to the second way of adapting LLMs, which is prompt engineering. Hey, everyone. We'll continue learning about different techniques to adapt a general-purpose LLM to a domain-specific LLM. In the last lecture, we learned about fine-tuning, and we saw that how by continue training a base model on our documents or knowledge base, we can get a specialized model that is capable of answering very specific questions. In this lecture, we'll focus on another important and very popular technique called prompt engineering. And we'll discuss various techniques under prompt engineering, and also we'll learn how prompt engineering can be used to adapt the LLM to our specific use case, which is a retail store. So let's start. So what is prompt engineering? At a very high level, prompt engineering is basically a way to craft or design prompts so that we can extract the desired output from the LLM. So it's very simple. Normally, a workflow is like this. We have the prompt, which is a user's query, and it goes directly to the LLM. And then the LLM processes that prompt and outputs some response. And this is the response that is being shown to the user. Now, in order to incorporate prompt engineering, we'll change this simple workflow by adding this yellow rectangle here. We'll call it prompt engineering. And it's just a logic that changes the user's query prompt. It takes that as an input, makes some changes or additions to that, and the output is another prompt. And now this new prompt goes into the LLM, and then the LLM generates response. So the only difference is that we are not going to pass the raw user's query to the LLM, but we are going to make some changes to it or make some additions to it, and then pass the new prompt to the LLM. Now, this is at a very high level what prompt engineering is, but there are a lot of techniques under prompt engineering. For example, we have few-shot prompting, zero-shot prompting, chain of thought or COT prompting, which is very powerful, role-specific, user context, and probably there are other examples too. And there are also more advanced algorithmic prompt optimizations, which makes this process more automatic. So in this lecture, we're going to focus on very popular techniques, including few-shot, zero-shot, and COT, to better understand what they do, how they do it, and why they are very powerful. And then after that, we'll see how we can use some of these techniques for our use case, which is a retail store. So let's start with few-shot prompting. To better understand few-shot prompting, I have some real examples, and I want to show how in practice it works. Again, I have hyperbolic service open here, and we saw that in previous lectures. It's basically a service that allows us to use some pre-trained models and send some questions and get some responses. And here I continue to use the base model, which we used in the previous lectures. And the reason for that is because base model is just a continuation model. So it continues the prompt. And I want to show that how powerful prompt engineering can be. And even in base model, it can influence the generation process. And then after that, we'll also switch to some post-trained models and see how prompt engineering helps there. So let's start with a prompt like, how can I learn machine learning? So, and let me also reduce this to 60. So before I press this, what we expect to see here is that it's just going to mimic what it has seen on internet. So it may just ask more questions, or it may not even directly answer my questions. It may include something that are irrelevant. Let me see how it responds. Okay, it's just very irrelevant. It's coming from somewhere probably on the internet, and it says, a few years ago, I was wondering the same thing. I had just started my PhD and so on. So it's obviously not answering my questions. And again, we were, in this case, it responded this way. If we ask again, it may just generate more questions. Let me run this again. How can I learn ML? What are the prerequisites? How can I learn ML? See, again, it's just asking more questions. Now, what I want to show next is that if we switch to few-shot prompting, we can actually force this model and influence its generated response to follow the format that we want. So for that, I have examples here, and let me just copy-paste this here. So what I'm entering here this time is I'm actually showing some examples to the model in the prompt. And then this way, I hope that the model would just follow the same format. So what I'm having here is that I have here this particular format, QA, and then I have a couple of random questions like, what is a good place to eat? And then the answer is Berkeley has lots of good restaurants. Another question is, what is the process of leasing a car? You can go to dealership and talk with a salesman. What is the capital of France? Paris. And then on the last line, I have my actual question that I want the model to answer. How can I learn ML? Now, this time, the difference is that the model is not really have all this flexibility to generate however it wants. it's going to follow this particular format. And this particular format is designed such that it actually answer my last question. So let me send this to see if it works now. I don't know why this keeps happening. All right. It's answering and it says take the class. And the reason that it's such a useless answer is because the examples that we showed are also not too comprehensive or not too helpful. For example, we say just go to dealership and talk with the salesman. And then as a result, the model is also telling us take the class. But basically, the important part is that even a base model can respond to our questions when we use few-shot prompt engineering, meaning that we show some actual examples to the model. Now, let me switch to a post-trained model, and I can choose Llama here, 405. So it's the post-trained equivalent of the base model. And then what I'm going to do here, I'm going to send this example. So this is what would we normally ask our questions. We would say, for example, if we have a math questions, we can have this, like John has 4 books and buys 3 more. How many books does he have? Now, in this example, the model would respond however it wants. We have no control over the generation process. For example, we may want the model to answer in a short format and just say 7 or something like that, but we have no control over it. So now if I send this, the model would probably say, easy one, John has 4 books initially and buys 3 more. So 4 plus 3 is 7. John now has 7 books, which is great. It's very relevant and it's really helpful. But let's say I don't want the model to answer this way. And I have another prompt here. What I want is that I want the model to answer in a particular format. And I have it here as an example. So I only show the model one example that, like, if you have 3 apples and get 2 more, how many apples do you have? And it just follows this format, answer and 5 here. Now, next I ask my real question. And what I expect to see is that the model would generate something like this. So it no longer would say easy one and lots of explanations and thinking and logics. So let's see if it actually works. All right, it exactly followed what I was hoping. So it's following this format. And this is why few-shot prompting can be very helpful, because it can basically guide the generation process and guide the LLM to generate something in the format that we want. Now, let me go back to the lecture. So we saw few-shot prompting, and then the next thing we want to talk about is zero-shot prompting. Okay, so few-shot prompting was showing some examples. Zero-shot prompting is not showing any example, and it still guide the generation process. So how does that work? Let's go back to the base model again. And then I ask the same question, how can I learn ML? And let me just decrease this to even lower, like 20. So for this, let's see if it asks more questions or not. All right, it's exactly asking more questions as we were expecting. Where do I start? I want to learn ML. Where should I start? Now, let's say I want to ask the same question, but now I want to use zero-shot prompting technique to guide the model to answer my questions instead of just asking more questions. It's very simple. What I'm going to do is here, I'm going to say, hey, this is Q. And then here is A. So with such a simple change, it's very likely now that the model would actually start responding to it. Let me try. All right, exactly as we were hoping. You can learn ML by reading books, watching videos, taking online courses, or attending bootcamps. So with some very, very minor changes and applying zero-shot prompting, we see that how we can change a base model to a model that can actually answer questions. Now, let's also go to the post-trained model, like Llama 3, 405. And I have another prompt here ready. And actually, let me not enter that because it's very obvious. So we'll just go over it. Another example of zero-shot prompting is that, for example, let's say we have a resume of some candidates, and then we want the LLM to extract the years of experience. So one way we can prompt the model is something like this: extract the candidate's years of experience from this resume. However, in this example, we have no control over the output. So we can rely on zero-shot prompting and enforce the model to output in a structured format. For example, we can say something like return only JSON-like, and in this format, years experience number from the resume or for the resume. Now, by just this simple change, now the model is capable of generating responses in the exact format that we want. So this is at a very high level, zero-shot prompting. We basically just write in the prompt as the instruction that we want the model to follow. We either include some formats as a hint, or we actually explain it in a text that, hey, do this in this format and make sure your output always follows this particular format. And this is zero-shot prompting, and it is very popular and used a lot. Now, the next thing that we want to talk about is chain of thought prompting. So chain of thought prompting is probably the most popular technique under prompt engineering. And later, it was a starting point for thinking models, which we would discuss in future weeks. But it is very powerful, and also it not only it helps at inference time in a prompt engineering format, but it can also help the model to actually learning to think during training. So again, for the training part, we'll learn that in future weeks. And in this lecture, we'll only focus on the prompting technique. So everything was started from this paper, Chain of Thought Prompting. It was released in 23, January 10th. By Google Brain. And then basically the idea here is that if we ask the model to answer something that is difficult, the model is probably going to fail. But if we show some examples to the model, and in the examples we show how to think in a logical, step-by-step way, the model would probably follow that. And if the model followed that, it would be able to answer correctly. And this is the example that they have, some mathematical question. And then it's basically few-shot prompting here. They say standard prompting. So what they mean is that they're not using chain of thought prompting, and they're just using few-shot prompting, meaning that they are showing the model a question and an answer, and then they ask their question. And then the question is basically the cafeteria has had 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? So the correct answer is 9. But the model is outputting the answer is 27 because it's exactly following this format, the answer is. And then it doesn't get enough time to think and reason. Therefore, it just throw a number, which is 27 here. Now, the idea behind chain of thought prompting is that instead of showing the model this very small, short kind of answer, we show the model how to reason and how to think. So the only change here is that instead of saying the answer is 3, they change this answer to something more logical. So for example, they say it started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 equal 11. The answer is 11. So this way, the model would learn to follow the same format, and as it's following the same format, it basically it pushes the model to think and figure out the correct answer like a step by step in a smaller computations. So here you can see exact same question, and then now the output is the cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 23. They bought 6 more apples, so they have 3 plus 6 equal 9. The answer is 9. So that's why it's very powerful, because it basically somehow indirectly teaches the model to think and to reason. So this is very powerful. And here they're having some evaluation metrics, and they're saying that the solve rate, it goes, especially in mathematical problems, it becomes significantly better. So here, yellow is basically their Palm 540 billion model, and they're using a standard prompting. And then the solve rate is 18%. And by just switching to chain of thought prompting, meaning that the model is exactly the same, all the weights and parameters are the same. We are not training anything. We are just using the same old model. But now, instead of asking our questions, normally we would show an example with chain of thought answer. And by just this simple change, the model would be able to improve its performance. And solve rate now becomes suddenly 57%. So this is where chain of thought started initially, and it's very interesting paper. You can take a look. There are more examples in different benchmarks how they are teaching the model to think and reason. And then so that's chain of thought prompting. And we saw the examples in the paper. I have also more examples here. For example, if you show the model, you have some mathematical questions with one letter or one token answer, the model would follow that, so it may fail, especially if the questions become more difficult. But if we have some reasoning traces and some logical explanations, the model is very likely to do better. And then remember, so this paper came out on January 10th, and it was basically a few shot chain of thought prompting, because we are showing some examples in the prompt, so it's few shot. And it's chain of thought because those answers are having reasoning traces. Now, 9 days later, this paper came out. 19 days later, this paper came out from Google Brain team. And now the only difference is that they're saying that we can also have chain of thought, but in a zero-shot format, not few-shot. So basically, what they're saying is that we don't necessarily need to show some examples to the model, so it reasons. And again, it's very interesting paper. You can take a look. Let me go back to our lecture because I have that here. So they propose a very simple change. They're saying that we don't have to show all these examples. What we can do instead, we can ask our question and we can just say, let's think step by step. And that's it. And just by this simple change, we are guiding the generation process of the LLM, and we are pushing the model to think step by step. And what that means is that the model would try to break the task into a smaller logical pieces or reasonings, and then it tries to just come up with the calculation step by step. So it's very interesting observation that just by adding this line of like five words at the end of each prompt, they would be able to get a lot better responses. Here you can see they're saying that this is few shot and then zero shot. And this is few shot chain of thought, which was this previous paper. And then they are proposing zero shot chain of thought, which the only change is let's think step by step. And now by this change, you can see how the model is actually generating a response with some reasonings. And again, this is the zero shot version of that. So same question, just zero shot. So the model only outputs 8. But now here, the model just keep reasoning over this question. So that's a very interesting observation. And this is zero-shot COT. And again, later, this became the foundation to build thinking models and training models such that they can think. And we'll go over that in future weeks. But again, yeah, that's chain of thought. And it's very, very popular and very, very powerful because it makes a big difference. Without chain of thought, for many difficult questions, the model may not be able to answer. But with just chain of thought, the model would be able to answer because it can just break down the task into smaller pieces and then solve the task step by step. So we also covered chain of thought, and there are also more. For example, we have role-specific prompting, which we would briefly cover. But we are not going to cover every single different way of prompt engineering. There are lots of different methods. If you search Google with prompt engineering, there would be lots of articles, papers, and so on. These first two links are pretty interesting. It's this one is a Git repo, prompt engineering guide, and it has lots of resources and information. And then they have also a web version which goes over all these things, zero-shot prompting, few-shot prompting, chain of thought. And you can see there are a bunch of other ways of prompting, meta prompting and prompt chaining, tree of thoughts. Again, many of these we would cover later, but this could be an interesting documentation to take a look. Let's go to the role-specific prompting and understand why it can be helpful. So role-specific prompting is also very simple. Basically, the key idea is to assign a role to the LLM. So let's say normally when we have a question, let's say a tax kind of question, we can ask it like, how can I, and whatever our question is, and just pass it to the LLM. Now, role-specific prompting just adds this sentence before that and assigns a role to the LLM. And it says something like, you are an expert tax advisor. And then it includes the user's query. And just this simple change make the LLM work a lot better. So that's it. That's role-specific prompting. Now, we've discussed various types of prompting, like few-shot, zero-shot, instructions, providing instructions as part of the zero-shot. And then we saw chain of thought and role-specific prompting. And there are other kinds of prompting. And then all of these basically make the prompt a lot of additions to it, the initial user query. And because of that, prompts are generally having two components, the final prompts that are going to the LLMs. One is the system prompt, and one is user prompt. System prompt is hidden instructions provided to the LLM, and these are basically as a result of all these prompt engineering efforts. And then user prompt is basically visible query that the user types. So whatever the user types, it becomes the user prompt. And then all the prompt engineering works that we have, it becomes part of the system prompt. So it's going to look something like this. We have a system prompt, and system prompt can do specify roles, give instructions, provide few-shot examples, also ask for chain of thought, thinking, and so on. And then whatever the user types is going to become the user query, and these two will get combined and then passed to the LLM. And if you go to ChatGPT and also all other major chatbots, they have a place to specify your system prompt. Also here in Hyperbolic, if we switch to a model like Llama 405 billion, there should be a place where you can specify a system prompt. And I think here, it's here. So it says it describe your system prompt, and then you can just include all your instructions and role-specific prompting and examples and anything that you have in mind here. And then each time you would enter something here, your question would get combined with system prompt and then passed to the LLM under the hood. So the LLM would know about all these instructions every time you ask a question. So that's system prompt, just to make things more organized, and you don't have to each time include all those prompts as the user's query. And then we can just have it fixed, have it once in a system prompt, and then start the conversation. The user can start the conversation by just asking their question without any additional handling. So, and that's about the prompts. And the next thing I want to talk about is, we talked about all these prompting techniques, but let's now get back to our original problem. Our original problem was that we wanted to use prompt engineering to adapt a general purpose LLM to our very specific use case, which was a retail store. Let's see how we can do that. It's very simple. We can have some software here, a logic here, which is mostly focused around prompt engineering. And then we have a system prompt. And then basically prompt engineering is going to just take this question, combine it with the system prompt in a very particular format, and then pass it to the LLM. And then how is it going to do that? What we are going to do, how we are going to write this is basically, we are going to say, okay, whenever the user's query comes, concatenate or combine it with this system instruction. And what is this system instruction? Basically, we manually create this and we say something like, read the following documents and respond to the question. And what are these following documents? These are all the PDFs and knowledge base that we have internally for our company or for our retail store. So basically in prompt engineering, we manually go over all our documents or knowledge base. We include all those information and policies and whatever is basically listed there. as part of the system prompt here, or it could be also as part of the actual user's prompt. We can manually have a software to append it to the user's prompt. But regardless of that, whether it's going to be in the system prompt or user prompt, basically by using prompt engineering, we can include everything, every important information we have in our documents, and then include it in the context. So when the question comes, what is the refund policy? Now the LLM does not have to hallucinate, or it's not ambiguous anymore, because it's very likely that whatever this question is, it can be found somewhere in these documents that is basically the knowledge base of the company. So this is simply how prompt engineering works, and how we can use prompt engineering to make an LLM rely on our internal documents and data and answer questions. But there is one major problem with prompt engineering. The major problem is that in many use cases, for example, if a big company wants to build an LLM adapted for answering employees' questions, big companies may have millions of documents or millions of pages. So including, or even thousands of pages, including all those information inside the prompt is very costly. And a lot of times it's not even possible, because LLMs, when they are trained, they are expecting a maximum length of number of tokens in their input. So if we go beyond that, it's computationally not possible for the LLM to process that and output it. It's going to be computationally very, very expensive. So all these LLMs have some maximum length. It's often referred to as context length or context window. And then what context window means is that what is the maximum number of tokens that we can pass as input to the LLM. If we go beyond that, the LLM can no longer process it. So that's the main issue. If our use case has just a few PDFs, it's fine. Prompt engineering can work perfectly fine. But if we are having a use case with thousands of PDFs and pages and documents, this approach may no longer work, because this constructed prompt would be very, very long and maybe beyond the maximum context window. So, and because of that, we're going to switch to the RAGs, Retrieval-Augmented Generation, in the next lecture, and we'll see how RAG can mitigate this issue. Hey everyone! In this lecture, we'll focus on the third technique to adapt an LLM or a general purpose LLM into a domain-specific LLM, and that's Retrieval-Augmented Generation, or RAG for short. In the previous lecture, we talked about prompt engineering, and we also saw that how we can use prompt engineering and put together all the internal documents that we have in our company, let's say, inside the prompt, and then pass this new prompt to the LLM. So this way, the LLM has access not only to the user's query, but also all the available internal documents and knowledge base in our company. So this way, the purpose is that, or the assumption is that the LLM should be now able to answer user's query correctly based on the information given. However, the key limitation of this approach is that LLMs have maximum context window, meaning that the input prompt cannot exceed beyond a certain length. And most companies, most use cases, we have a lot of PDF files, and knowledge base is very, very big. So by putting together all the documents, it simply exceeds the maximum context length that is practical. So because of this, prompt engineering is not going to really work, especially in cases where there are thousands or even millions of PDFs available. So RAG is solving that issue. And our entire focus of this lecture is on RAG, its components, and how it solves that limitation. So what RAG does is, again, remember, previously we had LLM and we had this what is refund policy, and prompt engineering was just putting together all these document database and include it as part of the input prompt. In other words, it was just concatenating all this text with this user's query and pass it to the LLM. But the problem is there are thousands of PDFs and files here, so it becomes not practical. Now, what RAG does is RAG adds a new component here called retrieval. And the purpose of retrieval is that pass only the relevant documents to the generation or to the LLM. Basically, what it does is that retrieval looks at all these documents here. It also looks at the question and it figures out which documents or which parts of each document can be helpful or can be used to answer this question. And retrieval just outputs those pieces of text here. So retrieval basically narrows down from this huge document database to pieces of text called retrieve1, retrieve2, and retrieve-k that are potentially useful for answering this question. Now, this, along with the user's query, is passed to the generation or the LLM, and the LLM outputs. This way, we just narrow down the entire document database to a smaller set, and then we are no longer going to exceed the maximum window size of LLMs. So this is the high-level idea. There are a lot of details in the retrieval and also in the generation, and we'll talk about each of these in more detail. And we also talk about how to optimize and what are the efficiency optimizations that we can add. But this is the high-level picture of RAGs. It has two main components, retrieval, generation. Generation is nothing but the LLM, maybe with some additions which we'll talk about, but it's at its core, it's the LLM. Retrieval just searches over the document database and just narrows it down into relevant pieces. And the relevant pieces now are used along with the user's query by the LLM to answer. So let's start by focusing on the retrieval. Again, retrieval is just equivalent of a search problem. It's what we want. We want to search from our document database and find all the relevant pieces of text that can be potentially helpful to answer a question. And in order to build this retrieval, there are two steps. One is we build a searchable index from documents. That is more a pre-processing step. We have documents where we pre-process. We have some data structures in place. We go over those, pre-process those, and make sure we have a good index. And then the second part is when we actually want to use the retrieval. And in that step, the problem is a search, because now we have a user's query and we want to go to this index that we built and just retrieve all the relevant pieces or chunks of text. So we'll talk about both of these. I have some visuals here. This is the first step. We want to build a searchable index from documents. So we have some code or logic or data structure here. It takes all these document database and it builds an index. And this index is searchable, meaning that it is following some data structures that are very efficient and effective to search from. And then the second part is searching from the index at runtime. So when the user has a query, like what is the refund policy, it goes to this second part of the retrieval, which is search. And then this search component interacts with the index that we've built in previous step. And then it outputs all the relevant chunks or relevant pieces of text from the index. So these are the key two steps. And what we are going to do now, we are going to focus on this build index. We'll see how can we really go from this huge document database of PDFs and possibly diagrams, tables, images, HTMLs into an index. So this is typically done in 3 steps to go from basically this document database to the index. The first step is document parsing. Then we have document chunking, and finally we have indexing. So all these 3, if we follow them sequentially, we would be able to build our index. So let's see what is document parsing. So document parsing is simply to go from documents, which again can be PDFs, HTMLs, or things like that, into the extracted .text file content. So that's the whole purpose of parsing, the document parsing. We have documents, we have PDFs, and PDFs we cannot really provide a PDF to an LLM. At the end, we saw in the previous week that LLMs expect numerical inputs, and numerical inputs can be obtained by having some sequence of text, not a PDF. So the purpose of this document parsing is to go from all these PDFs to the actual sequence of text. And we'll also talk about other modalities, like what if they're image in the PDFs. But just for simplification, let's assume PDFs are text only. We'll talk about how to extend it to images. There are two main methods for document parsing. One is rule-based, which is less common, and to the best of my knowledge, it's not really popular these days. And then we have AI-based models. So both are doing something very similar, and their aim is the same. Basically, they want to go from this PDF. First, they identify all the layout, all the different components. So this is the first thing that this document parsing, whatever the algorithm is, does. So first, layout detection. For example, here we have the layout. So we know that here is the title, here is title, here is text, here is text. This is a figure. Title, text, figure is image, and the rest of it is text. And then the second step is text extraction. So once we know the layout, there is some algorithm to apply, like AI-based OCR methods and so on. And then those are used to extract the actual text from these layouts, from these rectangles. And it just put them together in a structured output like text block, and it's like the actual text. And then it just keeps doing something similar to all these different detected layouts, extracted text, and just create this structured output. So if you look at this structured output, it's just a bunch of text that were extracted from this document. And also for images, we can just include the coordinates so that later we can somehow index those images as well. We'll learn how we would index images. But for now, this is how we are going to convert all our documents, all our PDFs into a structured output. And there are different libraries and different algorithms for document parsing. One popular example is this DDoc. It's basically a library for automate documents parsing and bringing it to a uniform format. Again, it basically does the same thing. It's just a library. It goes from your documents, it converts them, and then it reads them and creates this structured output here. And then another very popular library, which is commonly used, is Layout Parser. It's also a unified toolkit for deep learning-based document image analysis. And it's an interesting repo, and I think there should be some demo videos here and full talk. Those are interesting to take a look, and also their paper. Let me click here to zoom in a little bit. So for example, if this is one arbitrary page of a PDF, this is the code. We can just easily import it and then use some of its internal models to detect, for example, images and draw box for layout detection and all those things, and also extract text using OCR-based methods. And then you see the output can be something like this. We have these red rectangles, and then it identified the titles, text, figure, table, and so on. And it also works with other types of documents, not only PDFs, like magazines, magazine scans, websites. It can detect text regions, image regions, and table region, and extract those. And same for historical documents. So and these are some sample codes. But again, my point is there are some great document parsers out there, and they are commonly used, and we don't have to really implement all this logic. We can simply use it. It's going to be just a few lines of code to go from our documents into a structured output in a text format. And also if there are images, also extracted images as well. So this is document parsing. And the next thing I want to talk about is the next step, which is document chunking. So what is document chunking? Document chunking is basically going from the documents, the extracted contents, a structured output, the structured output that we obtained from document parsing in the previous step, and then it just chunked them. So the reason for that is because a lot of these documents, it might be coming from an entire book or report. So they are too broad, and it may also exceed the context window if we retrieve the entire document. For example, if one document is a book and we apply document parsing and we get all the text content from the book, it's going to be a huge document. And we usually don't want to return that as a retrieved relevant item to the user's query because it's just too broad and also it's too long. So these are the two main problems of if we do not chunk documents. And because of that, it's very common to chunk them. And chunking means breaking documents into smaller and more manageable pieces. And we call each piece chunk. There are different terminologies there. But basically, we go from this into smaller chunks. And the advantages of doing this is there are a couple of advantages listed here. First, we can handle non-uniform document length. So we have different documents, and these documents may have different length. And it's not usually good if we have some very small or very, very long documents in our retrieved. Ideally, we want our retrieved content to have somewhat equal length. It also improves precision because now we can really find the actual text content or smaller piece within a document that is relevant to the user's query. The third advantage is it overcoming LLM limitations. Again, that's because LLMs require a certain maximum context window. And by just chunking them, it's going to be more efficient. And we don't have to include parts of the document that is really not too relevant or too helpful to answer user's query. And it's also optimizing computational resources because, again, at the end, it's very effective. We don't have to include parts of the document that are irrelevant. So this is document chunking, and there are some different algorithms for document chunking. We have length-based algorithm, and it simply splits the text into chunks based on the specified length. So we specify a particular length, and then it just scans over the text in one document, and as soon as it reaches a length, it would just split it. And this is very heuristic based, and the problem with this is it may split in the middle of sentences because it's just purely based on the length. So a lot of these chunks, may end up somewhere that is not really meaningful, or it's in the middle of sentence. The other algorithm is regular expression based splits. And they use regex to split the text based on some specific punctuations, for instance, like dots or question marks, things like that. This might be slightly better than length-based because we no longer split something in some like middle of sentences. But now the problem is it lacks the deeper semantic understanding of text. And that's because a lot of times some pieces of text might be about the same topic. Sometimes when we reach a dot, the topic might become different. And just by splitting the text based on, let's say, punctuations, it's not really handling the meanings of different chunks of the text. So it lacks that semantic understanding. And then the third algorithm or method, which is more useful and commonly used, is basically we use specialized splitters, like HTMLs or Markdown splitters. So these are specialized splitters that they split the text at element boundaries, such as headers, items, code blocks. So they're already built with having those particular documents in mind. And they're built knowing that those documents can have very complex structure. And they work well just because of how they're implemented. So this method is usually more useful for documents in structured formats, again, like PDFs, HTMLs, and so on. And again, we don't have to implement any of these in general. There are lots of good splitters out there. One popular example is text splitters by LangChain. And this is the documentation and some overview. And it can be an interesting read. There's some guides and so on. But again, at a high level, what they do is they go from this document into splits. And there are also other libraries. This is just one example. So back to our lecture. And then the other thing I want to share is that now there's some hyperparameters that we can tune. For example, LangChain has this chunk size, chunk overlap, separator, and so on. And these are specifying how to split the text. For example, when chunk size is 35, what it means is that ideally we want to chunk it such that each chunk is has 35 characters, for instance. And then the other is overlap. And this is because a lot of times we may want to overlap these chunks a little bit so that basically we do not, again, cut somewhere in the middle that is not too optimal. So for example, this is a real example of LangChain going from this text with these hyperparameters. And then you can see the output becomes these smaller chunks. And it also overlaps. For example, here it ends with form of, and then the second chunk starts from form of. So form of is the overlap between these. So that's it. That's all about document chunking. The next step is indexing, and that's what we are going to talk next. So I have indexing here. And basically, up to this point, we went from all our documents in different structures like HTMLs and PDFs, whatever, into smaller chunks. And each chunk is either some sequence of characters or text, or they can be like images, like coming from figures or tables and things like that. So for now, again, for simplification, let's focus on text. We will cover how to handle images shortly. So the purpose of indexing is to store each of these chunks in a data structure that is easy to search. And it's just simply a data structure. It's nothing more. And there are different ways we can do indexing. There are different methods. And then as a result, there are different search mechanisms, depending on how we index. For example, we have keyword-based indexing. We have full text indexing. We have knowledge graph-based, and vector-based. Let's briefly see keyword-based and full text, and then we'll focus on vector-based, because vector-based is what commonly used nowadays in practice, and it's very important. So we'll just briefly discuss about these, which are a little bit more traditional. And then knowledge graph-based, there are some interesting reads out there. I will include those. We are going to skip it because it's too specific, and there's only certain use cases that rely on knowledge graph-based indexing. And almost like 95% of use cases that I'm aware of all are relying on vector-based indexing. So let's start. Text-based, including keyword or full, is basically matching partial or exact query terms with the content of documents. So basically, during this indexing process, we index like this. For example, if these are the text, we follow some data structure, and one very good example is Elasticsearch, for instance, which takes care of all these functionalities. And then it builds an index. So when you want to search from it, and for example, you have a query, it can easily refer to this index and say, hey, these chunks are including your query. Either it could be partial match or it could be exact query match. And this is something, again, that the user can specify. For example, you can say, hey, give me all the chunks that has this particular keyword or has this particular sentence in it. And text-based indexing methods would just enable you to do that. Again, these are good, and these are what traditionally being used. But the problem is that it's not really capturing the semantic meaning of documents. For example, if you're using synonyms, then you no longer would be able to do any partial or even exact match, even if there are some documents that having synonyms of your query. So these text-based methods are, again, good for certain use cases, but they lack the semantic understanding of documents. And because of that, vector-based methods are used commonly. So let's see what is vector-based method. Basically, the idea behind the vector-based methods is that instead of indexing the text inside each chunk, we use some pre-trained models to encode text into some vectors. And these models are called embedding models. So let me step back a little bit, and first we understand what is an embedding model, how it works, and then we'll get back to this vector-based kind of indexing soon. So what is an embedding model? An embedding model, it's also a very common term in machine learning. It's basically an ML model that maps some input, for example, text, or there are models that also map other modalities like images or even videos. So they basically map their input text into a vector in high dimensional space. It's also called embedding space. And the way that these models are trained is that when they map text to their embedding space, it's a very semantically meaningful space, meaning that if two texts have similar meanings semantically, they would end up nearby in this embedding space. Their embeddings, their vectors in high dimensional space would be nearby. So the embeddings can capture the semantic meaning of relationships. And the idea of this first came, there was this paper, Word2Vec, and this is the first time, again, as far as I know, that this was visually shown that, hey, we can train some word models or embedding models that after we map each word, after training, we map each word and we look at its position in this embedding space, similar words would have certain relationships. For example, synonyms would be end up nearby, and there is some relationship. For example, going from woman to man would be having the same direction of going from queen to king. So this paper is here, again, in case you are interested to read. It's quite old now, but it was the start of something very important, which later turned out to be embedding models. And they have all these diagrams that I just showed you, and also they explain how they train and why after training they get this meaningful embedding space, that similar words are end up being nearby and so on. So yeah, you can just take a look at this paper. And after this, basically, this is what we can do. We can just rely on some embedding models, not Word2Vec, some advanced models. There are lots of models available these days. We can use one embedding model, and then we can go from all the chunks that we had, text chunks, and we encode them. So what that means is that we would have a table like this. We have the one column is the text, for example, to learn more about our products, contact this number. And then it just gets mapped to this embedding space. And there is a point in this high dimensional space, and this is the point. So in other words, we are mapping each text, each chunk, to a vector, a numerical vector. And again, remember, these numerical vectors are semantically, like the relation is semantically meaningful in the embedding space. So if two vectors are nearby, it means that their meanings are close or they're talking about something similar. So that's the part to go from the chunks to an index table. Now, again, I mentioned there are lots of embedding models these days. For example, OpenAI has an embedding model, which is quite good and often used. It's called Text Embedding 3. And you can just pass something and get the embedding. And those embeddings can be stored, and those can be used to form our index table. And again, there are a bunch of other embedding models. I just searched Google. I don't know if they're really the best ones or there are better ones now, but just wanted to show some examples. So we have OpenAI Text Embedding 3 Large, and then also Gemini. So Google has its own embedding model, and there are all these different models available. And this is the output dimension, meaning that this is, so after we map the text, this is going to be the length of the embedding. So for example, OpenAI Large has 3072 numbers in it, in their embedding vector. So back to the lecture. This is the idea behind embedding model, and also how we use an embedding model to convert these chunks and build an index. Again, in the next video, we will talk about how this enables us to search from at runtime. But for now, our focus is on only building the index. So, and this is how we are going to build the index. We are going to use some text embedding and just build this table. All right, so we talked about text, and now the question is, what if some parts of our extracted content or some of the chunks are not text, they're images? And it's very common because a lot of PDFs these days, or even HTMLs, might have diagrams or some figures or some images. And it's very important to somehow encode those images as well, so that when a user asks a question, we can also rely on those images as well to answer their question. How do we do that? There are two ways. There are two options. First option is we use an image embedding model. Very similar to text embedding models, we have some image embedding models. And what they do is they train this model such that the input is now image, and then the output is the same embedding. So they are mapping each image into a high dimensional embedding space such that similar images end up nearby. For example, here you can see auto, we have cars here, so they're nearby, and truck here. And then like animals seems to be here, like dog, cat, and so on. So these are image embedding models. And it also started the first model that was widely used in industry was the OpenAI's CLIP model. And what they did was they trained a model using some contrastive pre-training method. And again, their paper is available. This is their repo. They explain exactly how they train. But at the very high level, the model has two encoders, text encoder and image encoder. And they train all these, both these text encoder and image encoder together. And their data is basically pairs of images and their corresponding caption or corresponding title. And then this is trained such that the learned embedding space is also meaningful. It's basically shared embedding space, meaning that now when you map a text to this embedding space and also an image which is relevant or similar to the text to this embedding space, their embeddings are going to be nearby. So this is another example of using an image embedding model. And one thing to note is that it's very important if we want to map images into some embedding space, it's very important to use a model such as CLIP that has a shared embedding space and use the exact text encoder for indexing our textual chunks. Because otherwise, there is no relation between image embeddings and text embeddings. So if we want to also map images, we use, for instance, CLIP. Text encoder is being used to build our text index, and then its image encoder part is used to build our image embedding index. So that's about CLIP, and that's about how to handle images. But this is option one. There is also another option we can use instead of relying on image embedding models. The second option we have is we use some captioning model. And captioning model are the ones that you pass some image to them, and then they describe the image, and they generate a caption for it in a textual format. And this way, we can basically first go from image to caption using this captioning model. You can see in this example, we have the image shows a cat sitting on a whatever and the rest of it. And now we use this chunk instead of this image to index. And now we can use our original text encoder to encode this image, because now we only encode its corresponding caption. So both options are available to build our index tables. We discussed both option one, which was using a model with shared embedding space. We use the image encoder to map images and build the index. And we use text encoder for textual chunks. We can also use option two, which means that we can use any text embedding model that we want. And for images, we can use image captioning to go from image to text, and then from text, we can just encode it to the to build the index. But regardless of which option we use, at the end, we would end up with something like this. We have converted all our images and chunks that were extracted from the documents into two indexes. One is image index, another is text index. And these are under the hood just tables. They're table like this. For example, chunk one, this vector, chunk two, this vector, and so on. And these are for images. And then for text, very similar. Chunk one, this vector, chunk two, this vector, and so on. So this is how we pre-process the entire documents, and we go from the raw documents such as HTMLs or PDFs into an actual indices, image index and text index. So we've covered all steps of, let me go back here. Okay, we talked about this building a searchable index from documents. Now, next, what we are going to talk about is now how can this index help us to search from at runtime? All right. So far, we talked about retrieval, and we also saw that retrieval is a search problem. And we saw how can we build a scalable index from our documents. Once we have this scalable index from the documents, now the retrieval is ready to be used, meaning that we can now use some algorithm to search from this index at runtime whenever there is a query. So let's zoom into that and better understand the detail. Again, in the first step, we built our index. Now the focus is going to be on the search and understand how search works, meaning that when there is a prompt, like what is the refund policy, and this algorithm, this component has access to the index, how can it efficiently find most relevant chunks from this index relevant to this and output it. So that's the focus of this lecture. So how do we really search? For a given input text, what we want to, again, retrieve relevant chunks of documents efficiently. To do that, we can use the same text encoder that we used to encode the texts. And first, we encode the user's query, which is what is your refund policy. And the output of this is just a vector, an embedding. Now, remember, we used a text encoder model that is trained such that similar sentences are going to be nearby, meaning that their embedding vector is going to be nearby in that embedding space. Now that we have this embedding of the user's query, it's time to find the which other embeddings are very similar to this. So that's why it's called a search problem. And it's basically a nearest neighbor search, meaning that given a query input or a query point, we want to look at all other points which are associated with text chunks or even image chunks and find the ones that are closest to this point. And we define some distance measure or some similarity measure. And a lot of times we can use things like Euclidean distance, cosine distance, and those formulations to find the distance between 2 points in this embedding space. And cosine distance is a common metric to use to measure the distance of 2 points. So we use something like cosine distance, and then we just compare every single embedding from the index with this query embedding, and we find the closest ones. And once we have the closest ones, we can now go back to the original chunk of text and include those as the output of this process. For example, these could be some different chunks that are extracted from the original documents. Something like our refund policy to return or replace an item and blah, blah, blah. After 30 days, you may get a store credit and the rest. And it is important to note that items should. So these are basically chunks of text obtained from documents that their embedding are very similar to the embedding of this question, which is what is your refund policy. So this is how we run search. And this is ideal because now we can simply pass this along with the user's query to the generation, which we'll talk in future videos. But now let's inspect this nearest neighbor search. We understand how can we really find the most similar embeddings to a query embedding. So this is a very traditional and common problem in computer science. Basically, the problem is given a bunch of points in high dimensional space. This example is just 2 dimension for simplicity. And we are also given an E of Q, which is the query embedding or the point representing the query vector. And what we want is that we want to find the top k most nearest points. In this example, if k is 3, we want to return these 3 points. Now, there are 2 different categories of algorithms for nearest neighbor search. One is exact nearest neighbor, and then another is approximate nearest neighbor, or ANN. And there are also other categories within ANN. Let's start with exact nearest neighbor, and then we'll talk about ANN. So exact nearest neighbor is basically, I think I don't have any visual for that. It's very obvious. Basically, this is the exact nearest neighbor. Basically here, the goal is to look at all other points in this space and find the top 3 closest points. This is basically guaranteeing that the return points are exactly the top 3 closest points to this query point. Now, the problem with exact nearest neighbor is that it's computationally expensive, especially if there are lots of points. So lots of points means that we have lots of chunks, and as a result, there are like very large number of points in our embedding space. And that's usually the case in RAGs because, again, the knowledge base or the internal documents that we have after we do chunking and they map the chunks to embeddings, there might be millions or even billions of data points. And comparing query with billions of data points each time is going to be very expensive. And that's why we have approximate nearest neighbor algorithms. And basically, the idea behind approximate nearest neighbor is that we don't need to necessarily return the absolute closest points, but if we return something reasonable and reasonably close to EQ, even if they are not the top 3, it should be still fine. So basically, it's an approximate version of the exact nearest neighbor. So let's see how some of these big category of algorithm works. We have lots of different algorithms, and all of those can be categorized into one of these 4 buckets. One is clustering based. Another is tree based. We have also locality sensitive hashing. And there are also other methods like graph based and so on, which we are not covering because of their very specific use cases. But let's understand how basically these categories of approximate nearest neighbor algorithm works. Clustering based ANN basically cluster the point once. So we have all these clusters. For example, we have cluster here, this cluster, and we have all these 5 clusters. And then we also have a representative point from each cluster. It can be usually the centroid. So let's say we have a representative of each of these clusters. Now, when a new query comes and we want to find the closest top k points to it, first we find which cluster it belongs to. And then we only search within those clusters. So this way we sacrifice accuracy a little bit, but instead we don't have to go over all data points or billions of data points. We can only go over the data points within that cluster. For example, if a query comes, let's say here, which I have my, my cursor here. So we would discover that this query point belongs to R1 or region 1 or cluster 1. And then we would search for the top 3 points, which is going to be this, and this. However, this point in R2 might be even closer, but again, we are sacrificing a little bit of accuracy for efficiency. And in practice, it works usually fine, and it's in most use cases, it's fine to sacrifice that little bit of accuracy. So this is clustering based, and the other category is tree-based approximate nearest neighbors. And these algorithms at a high level basically partition the data and form a tree. So basically they go from the entire data space into subspaces. And then this way, then they have these leaf nodes, which corresponds to regions. Now, when a query comes, they can just traverse this tree and they see which region it ends up with. And then that region is basically the region where we can just look over all the points. And these two can be related somehow, because when we are forming a tree, in some sense, we are just dividing the space, the high dimensional space, into regions. But there are different algorithms, and some of them are more purely focused on tree-based structures. And then the other category is locality-sensitive hashing. And basically this method, at a very high level, if I want to just give an overview, it uses some hashing functions that are a little bit different from normal hash functions. And the way that they're different is that if 2 inputs are similar, their hash function would be also the outcome of the hash would be also similar. So these functions are designed, again, they are designed such that when 2 inputs are close or similar or relatively similar, their hash output would also be similar. And this way, if we have such functions, it's very easy, because now let's say the space of hash function is 5 buckets, let's say, 1, 2, 3, 4, 5, 6 buckets. And then as a pre-processing step, we can just apply the hash function to each of our data points, billions of data points, and we find their bucket by applying the hash function to these points. And once we have this pre-processing, now when a query point comes, we can easily apply the same hashing function to see which bucket it belongs to, and then only search the points within that bucket. So again, all of these algorithms are following something very similar. They just try to find a way to organize the points such that at query time, we can only look for nearest neighbors within a certain cluster or bucket. So that's how we can efficiently run nearest neighbor to find the most closest, like most similar chunks to a query or text prompt. And this is the overall workflow. Basically, the text prompt comes here. It goes to the same text encoder. And then the embedding here goes into this search algorithm. And then, again, there could be different complexities. It depends on how we design our searching system. So let's say we have inter-cluster search. It's kind of clustering-based method. And then these methods first try to find the clusters that this embedding, basically this text prompt, belongs to. And let's say it finds out that it's here. Now, the next step is this intra-cluster search, which searches only this cluster and finds the most relevant or closest points. And then once it knows the closest points, it can return their corresponding data chunk. So here we see retrieve.doc1, retrieve.doc2, retrieve.doc. And each of these are basically a chunk of that document. And all these are based on these points are coming from the index images and index text, which were the result of our data preparation process to go from our documents to index. So that's all I wanted to cover for search. And the main thing to review is basically just efficiency discussions. That exact nearest neighbor is not optimal, so we can use various algorithms of approximate nearest neighbor, and then we can efficiently find most relevant text pieces and image pieces, and then we can just return them as the retrieved item. Now, as always, we don't have to really implement these approximate nearest neighbors. There are lots of libraries. Different companies have implemented those. I know Google has Scan, and Facebook, which is very popular, has Face. And basically, Face is exactly that library. It's basically a library for efficient similarity search and clustering of dense vectors. And these dense vectors are those embeddings or representation of our data chunks. So basically, there are lots of algorithms, and we can easily use them. And there is a documentation here on face.ai. So it explains, similarity search. They talk about various distance metrics that we've discussed, such as Euclidean distance, cosine distance, and so on. And then here they mention how to install it, and then how, various documentations and diagrams. So that's it. That's all I wanted to cover for search. We also learned building our pipeline. So at this point, we are over with the retrieval component of RAG. So back to the original RAG, we exactly know how this retrieval works and how we can build an index, and also later efficiently use some search algorithms to retrieve relevant documents. Now, the next thing that we want to talk about in the next lecture is the generation component. And now we understand what are some details about it and how can we even improve it. Hey, we are getting closer to wrap up RAG, and in this video, we'll focus on the generation component. So we'll just ignore this part, which we already learned about the retrieval, and we assume that the retrieval can retrieve some relevant chunks. And now we'll focus on this generation piece. And it's very simple, so it's going to be short. So at its core, again, the generation is an LLM, just a pre-trained LLM, a general purpose LLM. And what we do is that once we have the retrieved content from the retrieval, it gets added and combined with the user's query, which is what is the refund policy. And this way, we form our prompt. And the prompt simply goes into the LLM, and the LLM generates some output. However, in practice, we can make this generation a little bit more advanced, and that's going to be this workflow. So we can just combine it with a prompt engineering, which we learned as the second technique for adaptation. Basically, the main difference here is that now this generation has these both components, prompt engineering and LLM. First, the retrieved content as well as the user query goes into the prompt engineering, and then we apply whatever is necessary and helpful. For example, we can add role-specific prompting, we can add chain of thought prompting, and other things depending on the use case. And then prompt engineering, again, the output would be a new prompt, as we learned last time. Now that enhanced prompt or the engineer prompt would go into the LLM, and LLM would just normally process that and output the response. And again, prompt engineering, we can combine all different techniques that we learned. This can be one example, but this is just an example. For example, the prompt engineering can just convert all those retrieved contents as well as the user's query to something like this. This is an example. This is not necessarily related to retrieval or RAGs, but basically we can have user's initial query here. We can have context from search if we are doing some searches. In this case, it's basically probably the retrieved items. And then here we do role-specific prompting, like you are a helpful assistant who answers company name, internal questions. And then here some instructions. Your task is to deliver a concise and accurate response, and so on. We can also do few-shot prompting, show some examples that this is how you cite, or things like that. We can do chain of thought, zero-shot chain of thought prompting, and by saying if there is a reasoning process to generate the response, think a step by step and put your steps in bullet points. And then finally, we can have user context prompting, something like this. This is basically just to show that after we apply prompt engineering, we convert those raw retrieved content as well as user query into something more structured and more specific and helpful for the LLM to generate response. So that's it. That's the generation. It's simply an LLM, and we can combine it with prompt engineering to improve it. Now, one important thing that I want to note here is that, remember, this is the general purpose LLM. So if our retrieved items are not really accurate or is not too helpful, this LLM may fail. So for example, let's say we have a retrieval and our retrieval or embedding models that we are using are not too accurate. So that means that some of these retrieved items are not necessarily too helpful to answer this question, or maybe irrelevant. Now, LLM has no idea. It basically has all this information, and it thinks that all these are helpful or can be helpful to answer this. So it may just produce some answers that are not necessarily accurate. So we can go one step further and also fine-tune this LLM. So basically, this way we are combining all these methods that we learned, fine-tuning and prompt engineering and RAG, to improve our generation process. And this is a very tricky training, and there is a very good paper called RAFT, and I think it stands for Retrieval-Augmented Fine-Tuning. So the idea is, basically, again, the motivation is if retrieval quality is not good, LLM will generate suboptimal outputs. So we want to fine-tune LLM to distinguish between relevant and irrelevant documents. So that's the key idea. Basically, the idea is that we label some relevant and irrelevant retrieved contents, and then we continue training the LLM that we have. And during this fine-tuning, the LLM is basically trained to generate responses based on relevant documents while minimizing the influence of irrelevant documents. And you can see the workflow here. Again, I described at a very high level what it tries to do. It tries to learn which retrieved documents are relevant, which ones are irrelevant. So during the generation, it would rely more on relevant documents and ignore irrelevant documents. And if you're interested to learn more about it, this is the paper. It was published in 2024. And it explains all the details, how they are training the model, and it's an interesting read. And it also discusses, training time and how they prepare their data and, RAG top K and why it improves the performance of RAG. So that's it. That's all we can do, and we can push the generation to get the best possible response that we are hoping for. We can combine it with prompt engineering, and we can also fine tune so that it knows which retrieved documents are relevant and which ones are irrelevant. So that's generation, and we are done with the architecture and design of RAGs. In the next lecture, we'll learn about evaluation of RAGs and how should we evaluate and what are some of the important metrics. All right, we are getting closer to wrap up RAG. And in this lecture, we'll focus on the evaluation. As you can imagine, there are different components involved in RAGs, and therefore the evaluation is more complicated. So there is not a single or multiple metrics that we can easily use to evaluate RAGs. There is this retrieval component and how accurate the retrieve items are. And then when the LLM generates something, there are different aspects, like how accurate the generation is. Is it hallucinating? Is it factually correct? Or is the generation aligned with what was given in the context, or it's different? So all these different aspects basically makes the evaluation more complicated. But the evaluation can be described in this figure. We have query, we have the result or the generation, and then we have the given context to the LLM. And then we can evaluate this RAG system from different perspectives. And each perspective is involving some of these components. So these are some of the key aspects that we generally evaluate RAGs. One is context relevance, one is faithfulness, one is answer relevance and answer correctness, which is relating between the result and query. And again, by just looking at this figure, we should have some idea about why each of these aspects are important. So let's just quickly go over them. First, we have context relevance. And again, here we have context relevance between query and context. So basically here, what we are trying to measure is that how accurately the retrieval component selects relevant documents based on the query. So this is basically tries to evaluate in a ranking-like system. Basically, what we want to know is that if basically given the query, are the retrieve components relevant or not? And this is actually measuring the quality of the retrieval component. And for that, we have these evaluation metrics, which are mostly used in ranking systems. And again, because context relevance is kind of ranking, we want to know that given the correct answer, were we able to retrieve those in the context or not? These metrics are also ranking metrics: hit rate, MRR, NDCG, and precision at K. Again, if you are interested to learn more about the details of these metrics, each of them have really great, wikis, and there are some papers for some of these. And feel free to take a look to understand how they're designed, what is the formula, and so on. But at a high level, these are ranking metrics. So they try to measure how good our retrieved items are given the correct answer, or given the query. Basically, it depends on how we define it. So this is context relevance, and then we have faithfulness. Let's go back to here. Faithfulness is to measure if the results are faithful to the context, meaning that if the generated response is actually coming from the provided context, or it's just something different or hallucination. And this is a difficult type of evaluation, so it's very subjective. So humans are usually needed as part of the evaluation, or we can rely on fact-checking tools and consistency checks. Again, I have some example here, but the main goal here is that whether the generated response is factually aligned with the retrieved context. We want to know that if the generation is aligned with this context that were given to the LLM. And then finally, we have answer correctness. Again, let's go back to here. Answer correctness is trying to measure if the result is correct given the query, if the generation is relevant to this query. So here, basically, it's a The metrics we use are basically the ones that are used to measure the quality of generative systems like caption generation, like those kind of systems. And these metrics are mostly used for those purposes. So here, again, we have the prompt. And then the goal is that we compare the generated response with the correct response, and we see how aligned they are, how close they are. And then these are some of the metrics to compare two different sentences or paragraphs and measure how similar they are. So this is all about evaluation of RAGs and different aspects of it. And for each aspect, we also saw various metrics. Again, if you're interested, for most of those metrics, there are dedicated papers and lots of tutorials online. If you're not familiar with, you can just review those. But this is how we evaluate RAG systems at a very high level. Hello, everyone. This is the last lecture of week 2. And in this lecture, we'll just put everything together and review the overall system design of a RAG system. And it's basically just, we are basically just putting together everything that we've learned. So we saw the indexing process. During the indexing process, we go from our document database, and these are the internal knowledge base for our retail store, let's say. It's a bunch of PDFs, and it could be in different structures or like HTMLs, markdowns, anything like that. We have document parsing and chunking, and then we apply a text encoder or text encoder and image encoder. These are coming from a model like OpenAI's Clip model, which have a shared embedding space both for text and images. And then we build these indices for index for text and index for images. And this is just a table. It's nothing, it's not too complicated. It's just a table with ID of the chunk and the actual embedding of that chunk. So that is the indexing process. We do it once offline on our data, and we build this. Now, every time there is a query by user, first we have some guardrails again here, or we can call it safety filtering. There are different terminologies. These days, it's mostly referred to as input guardrails. And we have also another output guardrail. But again, the purpose of these two is to just ensure that the system is going to be safe, meaning that if there is a request that is not going to be safe to process, the system do not assist with that. And similarly, if the request is safe, but somehow the output is not safe, or it's not, it's biased, for instance, it would, the output guardrails or safety filtering would discard the request and not show the final response to the user. So these are these two components. Then we have query rewrite or also query expansion. The purpose of this is to improve and enhance the provided query by the user, because a lot of times the initial query may have some problems. It may be ambiguous. There might be missing punctuations. There might be some grammatical problems. So this is what this component does. And then after we have this final enhanced user query here, first it goes to the text encoder to get the embedding. Then this nearest neighbor search, which is typically an approximate nearest neighbor, finds all most closest embeddings to this user query, like enhanced user query coming from here, and find all those relevant chunks. And those can be text chunk or image chunk. And then all of them are passed as the retrieved content to the generation along with the enhanced prompt. So first, prompt engineering, add whatever like role-specific prompting, few-shot prompting, chain of thought, and make it a very nice, comprehensive prompt. And it would also include all the retrieved content. And then the retrieved content would go into the LLM. Now, this LLM could be a general-purpose LLM, or we can fine-tune that using Raft method to have a more accurate LLM. But regardless of that, we'll just use our LLM here, either the general purpose one or the fine-tuned one. And then the LLM would just process the given prompt and output, and the final response is shown to the user. So this way, we have control over this LLM, meaning that we can just, whenever we have more PDFs or more new knowledge in our knowledge base, we can just add everything here, we can index it, and then from that point on, anytime there is a user query, this whole system would take into account those newly added documents as well. So it's very easy to just add or remove some documents from this system. And similarly, RAGs are also useful to get live data. And we'll learn more about that in the next week when we talk about tool calling and search. But basically, still, RAG can be very, very useful because when a request comes here, if we have another component which searches the web and gets some live data, in a very similar way, that live data can also come get to this retrieval component, and relevant parts can come here. And this way, the LLM would always have access to live data. But again, we'll learn about search and tool calling in the next week. And this week, we can just wrap up our RAG topic. So yeah, that's it.